All right. This presentation is called Vine Nutrition. So there are essential nutrients, essential elements. There are 17 elements that all plants need, and grapevines are in that category where they need these 17. And if you've taken plant science already, you should already be familiar with the 17 essential mineral elements, which includes 14 nutrients. The first three are essential, but they are not considered nutrients. So there are three criteria to be considered essential. How do you know it's essential? It can't be completely substituted for another nutrient. So in some cases, one element might suffice to fill in the gaps for another. Therefore, it is not considered essential if it can be replaced. A given plant must be able to complete its life cycle from seed to seed. And if that nutrient is missing or that element is missing, it can't complete its life cycle. And it also must be a component of an essential plant constituent, something that is essential for the plant itself. So, for example, if there was, and I'm just making this up, a particular element that caused a color change in the flowers, if the element is present, the flowers are a different color, and that color might improve pollination. So that wouldn't be the case for vines, for grapevines, but I'm imagining any other plant, maybe bee-pollinated plant, that if a particular nutrient is, or a particular element is available, it might be preferentially pollinated by bees. That would make the element beneficial, but not essential. It wouldn't be essential because even without that nutrient available in the environment, it would still survive, it would still go to seed, it just wouldn't be pollinated as efficiently. And I just made that up as an example. I don't know of an example of that specific scenario, but just to give you an idea of something that might be beneficial versus essential. If it couldn't be pollinated, there was something that prevented pollination without that nutrient element, then it would be considered essential because it cannot complete its life cycle. It can't make seed. So fertility management, the three main elements that are not nutrients that a plant needs to survive are carbon, hydrogen, and oxygen. And those are the same three that animals and bacteria and protista all need to survive as well. Fungi, everything, every living thing on Earth is primarily made of these three things. We don't call them nutrients, just like I don't call it a nutrient when I breathe oxygen. It is essential that I breathe. I need that oxygen, but it's not a nutrient. It's just part of the backbone of my structure that I get from the environment. Plants are the same. CHO, CHO. And the two major sources of that, water and carbon dioxide. Carbon dioxide gives carbon and oxygen. Water gives hydrogen and oxygen as well. The oxygen we breathe is another source of oxygen as well for plants and animal life. So there are 6 macronutrients. The 3 primary macronutrients are N, P, and K. If you have a complete fertilizer, it must have N, P, and K, nitrogen, phosphorus, and potassium, K, in order to be considered a complete fertilizer. And they're called macronutrients because the plant needs lots of it. These aren't big nutrients. They're no bigger than the micronutrients. The only thing big about them is that they need a big amount. They need large quantities. They're still the same general size range for any other element, an atom, or a small molecule. That's all they are. And they're extremely, extremely tiny. at the edge of the best electron microscopes to see these things. They are so small, but they are considered macro because we need lots of them for the plant to survive. Now, the first three are considered primary macronutrients, not because the plant needs them any more than the other three, but the N, P, and K are the three we need to consider the most. We need to address the most. We need to focus on the most in order to grow crop plants effectively, efficiently, with maximum production. So we need to focus on N, P, and K to make sure the plants have enough. The other three also are needed in large quantities, calcium, sulfur, and magnesium, but they are often not necessary to be provided by the farmer because the farmer or the plant actually can get those directly from the soil without the farmer having to intervene. Now, with high production rates in modern times, we also look at these. We look at all of the nutrients with a very close monitoring. We're testing the soil, we're testing the tissues, and we're looking at all 17, or at least, depending on where we are, at least 10 of the 17 that we're really focusing on to make sure that they have enough. And maybe once we do some soil tests and tissue tests, we can determine that, yeah, I don't have to worry about a particular nutrient. There's so much in the soil, there's plenty in the soil, it's something that I can not worry about. But to get maximum production, we still, in this day and age, look at the other three secondary macronutrients: calcium, sulfur, and magnesium. Now, sulfur is highlighted here because if you are doing a complete fertilizer, it is sometimes included as a fourth nutrient element. If you see a complete fertilizer with 4 percentage numbers on the bag, the first one is nitrogen, the second one is phosphorus, the third one is potassium, and if there's a fourth one, that represents the percentage of sulfur. It is often added to a complete fertilizer, but not always. And sulfur is not required to be complete. So the 3 NPK, calcium, sulfur, and magnesium as the second 3. Those are the macronutrients. And then there are 8 micronutrients: iron, manganese, boron, copper, zinc, molybdenum, chloride, and nickel. Oh, actually, before I get to these, I did want to say something else about sulfur. There's so much sulfur that is used for fungus control that the farmer probably in a grape vineyard in this part of the world probably doesn't have to worry too much about adequate sulfur. The other ones are far more important to worry about. And so of the 6, sulfur's kind of down on your list of worries in a vineyard environment usually. There are exceptions, but it depends on your situation, your soils, etc. So back to the micronutrients. There are 8 micronutrients, and based on experience in the Central Coast area for some of the vineyards in our local appellations, the 3 that are most closely monitored are iron, manganese, and boron. Boron is probably the one with the narrowest window of sufficiency that is not going to cause a deficiency problem for the plants, and also not cause a toxic problem for the plants. For some plants, the amount of boron that you have that you need to grow one plant might be toxic to another. And so boron is one of those that's narrow. Most nutrients are pretty broad range. You just have to be close, somewhere in the range, and it doesn't matter. A lot of the modern philosophies of trying to protect the environment and your pocketbook is to use as little as you need to be in the sufficient range. You don't want to add excess because you're wasting money and it potentially gets into the groundwater or the surface water in your environment and causes environmental problems, especially with certain nutrients like phosphates can be a problem, and nitrates especially are a problem, with nitrogen getting into well water, etc. So right now the focus is on nitrogen, but that's not the only one that is environmentally damaging to an extent. So there are 92 naturally occurring elements. If you look at the periodic table of the elements, and I gave you one at the very beginning of the semester that you could look at, but out of those 92, 17 are essential for plant growth for all plants, and 14 of those are considered nutrients. So you subtract the CHO, the CHO, carbon, hydrogen, and oxygen, and you are left with 14 that are considered nutrients. And you can use these two sentences at the bottom to get all 17 memorized. And I would suggest you memorize one. Either A, C. Hopkins Cafe is mighty good with salt. Mnemonics are best with a cup of Zin. Zinfandel. This is a wine class, right? Oops. Or the second one, C. Hopkins Cafe, mighty nice cuisine managed closely by the mob. And if you look at the large capital letters in bold, they represent the 17 nutrients that all plants need. And there are a few others that certain plants need, like sodium or silicon, some that are beneficial, like vanadium or cobalt. But those aren't things we worry about with grapes, and I'm not going to worry about in this class. These are the 17, and I've listed them on previous slides, but the original, the one that's been around for decades, is just C. Hopkins Cafe is mighty good with salt. That's all it has, and it gets some of the major ones: carbon, hydrogen, oxygen, phosphorus, potassium, nitrogen, sulfur, calcium, iron, magnesium, and chlorine, but it misses 5 or 6 of the micros. And so I like these two at the bottom because it completes the list. So I've already mentioned micro versus macro. It has nothing to do with size. It has nothing to do with how much is in the environment, although there is a correlation. The micros tend to be in the environment in small quantities, but what it really is about is how much the plant needs to grow. So some things like iron, it's a micronutrient, but there's massive amounts of iron in some soils, way more than plants need. So it's not about how much is there, it's about how much the plant needs. Macronutrients, NPK, calcium, magnesium, and sulfur are needed in large amounts by plants. Micronutrients are needed in trace amounts. So sometimes you hear them called trace nutrients or trace elements because they only need trace amounts for the plant to be happy and complete its life cycle. But even within the micronutrients, even though they only need a little bit, in modern agriculture, we focus very carefully on the available concentration of these nutrients because we're trying to maximize growth, and we're trying to thread a needle with growing the perfect crop and maximizing profits. And we've learned a lot over the centuries of growing vineyards, and we are trying to make it better, more precise, and make those grapes have the perfect yield and perfect winemaking or table or raisin quality that we're looking for, whatever reason we're growing those grapes. So nutrient availability, how much of the nutrient is actually in the soil, is very different than how much is available to the plant, because what's in the soil is all there, but just because a particular nutrient element, the atoms are there, it has to dissolve in water in order for the plant to get it. It has to dissolve or be soluble. And if it's soluble and dissolves in water, then it can be taken in by the plants. And what nutrients are going to be soluble? depends on the pH of the soil. It also depends on the climatic conditions, temperature, and other factors, but the biggie is the pH of the soil. And it also has a lot to do with the cation exchange capacity of the soil. If you don't know what that means, look it up. It's just the ability to exchange positive cations with the plant. And so there's an exchange between the soil and the root through the soil moisture, exchanging cations. And that's how plants take up nutrients. And if you look at this chart, you have acidic soils on the left-hand side, alkaline or basic soils on the right-hand side, and neutral soils down the middle. And you can see the actual numbers from 4 to 10 on this chart. And the width of each of these green bars, or the height, I should say, the thickness of the bar represents how available that nutrient is. So for example, nitrogen is very available between pH 6 and about pH 8. But you start getting over pH 8 and it dramatically drops. Nitrogen becomes less available. Below pH 6, it also starts to drop. Phosphate, or phosphorus, which is in the phosphate form in the soil moisture, but the phosphate is actually in two forms at different pHs, and you can see where those two forms change right here in the pH 8 region. You start to change to a different form of phosphate, and the different forms are more or less available to plants. Something like iron becomes low available in alkaline soils, but very available in acid soils. Now, this is a gross approximation, and it's much more dramatic than it shows here, but it gives you an idea how pH affects nutrients. So something like calcium, calcium is actually very available in higher pHs. Now, this is pretty dang extreme. When you start getting above 9, you're rarely going to get above pH 8.5 or something in this range. A pH in the alkaline range of 8, calcium is very, very available, but it might be difficult to get iron, copper, and zinc. They're not as available, so the plants might have a problem. So there's a balancing act. You don't want to say, oh, I can just adjust my pH down to get more iron, or I can adjust it up to get more calcium. If you do it too far for any one of them, you're going to sacrifice the other. It's a balancing act, and you have to manage whatever pH you have within the limits of how much you can adjust that pH. And you can adjust it based on some factors, but you have to look at the soil. You have to look at what the pH is, what the buffering capacity is of that soil, etc., to determine, is it reasonable to be able to adjust the pH in this vineyard. Water availability is also very important. No water, no soluble nutrients. It doesn't matter how soluble they are, but the more water is there, the longer it's there during this growing period, the more that water can work on dissolving those nutrients that could be available and making them available. So no water, no nutrients. Now here's another version of that pH chart, a little more colorful and a little more dramatic in how it shows the availability. It's exactly the same thing as the previous chart, except it goes a little narrower range from 4.5 up to 8. So neutral is way over here on the right-hand side of this chart at pH 7. But you can see, I think, a slightly more realistic look at how dramatic the changes in availability are at these different pHs. Is this an exact chart? No, it certainly depends on other factors like water availability, like temperature, like other factors in your soil. The movement of nutrients into plants. It's a passive process by diffusion. When water is moving into the plant roots by osmosis, the nutrients are diffusing through the water, the soil moisture, and they move with the water. So as water moves into the roots, the nutrient elements that are dissolved in that are going to move by diffusion with the water and enter into the roots. No energy is required. Diffusion is just the passive process of things moving from higher concentration to lower concentration. And I won't get into the details. If you're interested, you could look at more of this a little bit more critically. For the test, I won't talk about apoplastic or apoplastic, excuse me, and symplastic transport between or among cells, within cell movements, etc. But this gives you an idea of how the nutrients are transported in some of the vocabulary for the transmission of these materials through the plants, through the roots from cell to cell especially. Again, for those of you who are interested in expanding your vocabulary and understanding, this is a slide to help you do that. For those of you who are most interested in trying to make sure you don't memorize too much to have a problem on the midterm or the final, this is something where you might want to slow it down. Let me take a quick break.